Welcome students. In this session, let us look at the structure of the McCullough-Pitts model of artificial neuron. As we have already seen, artificial neural network is made up of multiple small elements which we call it as neuron. It's not a biological neuron, but it is an artificial neuron. However, you can find the characteristic features exactly equivalent to that of a biological neuron. In a biological neuron, you will have many parts such as dendrites, you have soma, you have axon, input, output, and the processor. In the same way, in an artificial neuron also, you have the inputs and outputs and the processor. So now look at this diagram. You can see plenty of inputs available as given in this architecture. So how many inputs should you have? In a biological neuron, the number of inputs is enormous. It is not limited. In the same way, when you look at an artificial neuron also, you can have as many inputs as you like. It indirectly indicates that this artificial neuron based system can be used for any applications. The second is the processor, which you can find the two blocks within the oval symbol in my PPT slide. You can find summation and also activation function. So once you receive the inputs, it is passed through this summation block along with the alphabet W. Keep the alphabet W aside for the time being. Let me complete the processor, then I will come and explain you what is this W all about. So when you have the summation, you have the multiplied values put together for all x1, x2, x3, and you add everything together. Now this output of summation block is called as net value, which is indicated in this slide as YIN. This net value is again given to the activation function block. It is a function block, but technically speaking, it is called as activation function block. Once this activation function block is initiated, you are going to get the output. This is a structural arrangement of your artificial neuron. But the only missing piece in this structure is the alphabet W. What is this W all about? It is called as weights. Why do we connect these weights with the inputs? Remember, I have already told that all the inputs are not necessary to take a decision. Some inputs are extremely important, some inputs are partially important, and some inputs are not at all necessary. So this importance measure can be quantified by this concept called as weights. W stands for weights and it has a value ranging between 0 and 1. Whenever we say 0, it means it is not at all important. Whenever you say 1, it is completely important. And whenever you say 0.5, 0.3, 0.2, you have infinite numbers between 0 and 1. You can give that much weightage. So this is the concept of the weights. Now these are the mathematical equations for the theoretical explanation which I just gave. Yin is equal to x1w1 plus x2w2 plus x3w3 and so on. So your net input can be generalized using a summation symbol and also a multiplication symbol. Now this input or the net value is passed through an activation function and you are going to get the output. Now let us go in detail about what is activation function, what is weight and all the concepts. So this is a table which shows the analogy between your biological neural network and artificial neural network. An interesting aspect here is how can I equal weights in the biological perspective? The answer is synapse. So synapse is the biological interface point which is going to release chemical or it will not release chemical. If it releases chemical, then some process will be initiated, be it excitatory or inhibitory. It doesn't matter. When the chemicals are not released, that process is not going to be initiated. An on-off switch-like condition. Again, here in weights also, we make use of the exact concept, 0 to 1. So that's why we always make weights equal to synapse. Now let us talk about the activation function. What is this function all about? Do we have this activation function in the natural brain? The answer is no. There is no activation function in the biological neuron. but artificially we are inculcating that in our system to make sure that the handling capability of my system will not affect the processing part of the artificial neural network. Say for example, if you have a small system or a system with low spec, you will not be able to execute larger operations where you find that our net value is summation and addition. That means your value is always going to be on the rise. On the other hand, you can have a small spec, but if you can normalize your data between the range of 0 to 1, then you can make sure to use all those applications even with your low spec computer. That's why we make use of activation functions in our architecture. A simple normalization process is how you convert your data within the range of 0 to 255 to 1. How do we do that? Just divide it by the maximum value. It will give you for 0, it will give you 0. For 255, you will get 1. So intermediate values can be accordingly marginalized. So what are the types of activation functions? We have different types. One is linear activation function. The other one is rectified linear unit activation function. We have the sigmoidal activation function. We have the tangential hyperbolic activation function. But the important point you need to note down is all the activation functions are not used for all the applications. Classification, we can go for different. For regression, we can go for different functions. The same way, even between deep neural networks and multi-layer perceptron, the level of activation functions we use is different because the requirement from this activation function is different for different applications. In deep neural network, we predominantly use rectified linear unit, which we will be studying in the